Hello, my name is Daniel Lewiński, and I would like to welcome you to my today's speech titled Synergy Inc. Make your NPCs work like a good or bad team. So today I'm going to talk a little bit about the cooperative planning, and the agenda is such. At first, I will introduce you to a problem and explain why did they even bother doing that. Then I'll let you know how the algorithm works. Then I'll go through some core problems that I encountered during the development time of this solution, and which solutions got rid of those problems. Then I'm going to show you some code involving the architecture, which classes are there, what they are for, and so on. Then I'm going to tell you a little bit about interaction of this layer with your normal game AI, because it's not supposed to be a substitute for your normal game AI, just one additional layer. And at the very last, I have some ideas for potential improvements that I didn't have time to test or implement yet. So, who am I? Like I said, Daniel Lewiński. I'm an AI programmer. Very hard work to tell very quickly. I've been working for over 6 years at QED Games. Majority of my time spent there was working on our NPC, our tool for designing and developing game AI, especially for NPCs. I've also been doing some code development with our clients regarding AI in their games. And I've also done a bit of in-house game development. Those are a few games that we've worked on. I personally was involved with Tactical Troops, Hard West 2, and a little bit with Soccer Kids. And right now we're working with an unannounced project, which is a third-person fighting game. So yeah, let's go to talk about something actually important. Introduction. So we had an idea for a game called Fugitive 5, and it was supposed to be a turn-based stealth game with deterministic combat, but lots of imperfect information, and therefore it needed a lot of information gathering mechanics. And we're kind of famous for our AI, so we wanted to have a game with advanced AI. But unfortunately, as it turns out, the game wasn't really that good, and therefore is discontinued, at least for now. But it was still a good research sandbox for this project. Disclaimer is that everything I'm going to show you from the game is obviously coming from a prototype. There are some junky animations and so on. You'll have to live with that. And I would like to give some credit to my coworker Piotr Łukaszewicz, who helped me adjust the game a little bit, so you will know what AI is doing currently, what were their motivations when they're executing actions on the screen. And there is some problem with AI in stealth games that is very highly exploitable. Sometimes it's desired, but in my opinion, it's not in that way. It's very easy to separate enemy characters and just kill them one by one. And as we all know, nobody will notice if there is nobody to notice. And this is a short comic strip presenting such a situation where a player is killing enemies one by one. And as it happens, the situation is also present in our game. So yeah, we have a situation where I'm entering a building. One of the enemies saw me going there, is going to pursue me, and is going to instantly die killed by my Overwatch. It generated some noise. When I pass the turn to other enemies, one of them is going to investigate, and you guessed it, is going to get killed by an Overwatch. Yeah, so there's that. And I would like to get rid of that situation. So, possible solution I could come up with are, one, you can improve perception and memory. So, for example, if you have an agent that is locked in a room and is doing the patrol routes there, if they remember that all doors were closed, and when they are doing their routine patrols, they notice that suddenly one of the doors is opened, well, this is a situation that probably should be investigated because something uncontrollable happened. But the other solution, which I'm going to focus much more during this speech, is group behaviors. They could simply cooperate with one another and try to set traps for the player. to seem like clever entities. So, okay, there are to cooperate various entities, various agents. We need to allow them to plan their actions and allow to plan them specifically for cooperation. I'm going to briefly present you two algorithms which allow you to devise plans for your AI characters. One of them is GOAP, goal-oriented action planning. It uses what we call total order planning. It means that it returns a plan in form of sequence of actions, and they are strictly ordered. There is a first action, second action, third action, and so on, and they have to be executed in that exact order. So it doesn't support parallel actions. Therefore, it is not really a viable solution for this concept, because if you have a cooperation where they are still executing their actions one by one, it's not going to look very clever, so it's going to be problematic. And additionally, the goal state that is provided to the algorithm needs to be some sort of game state. So for example, if I needed to have my agents ambush the player character, I would need to tell them, okay, you need to be inside the building, player also needs to be inside the building, you have to see the player, and the player needs to be dead. That is the goal for the trap. It's a bit inconvenient. So the alternative approach is task networks, sometimes called HTNs, or a simplified version of this algorithm called STNs. And they use plans devised by partial order planning. And that means that plan is in such a form that every task has only is connected to other tasks by orderings. That means that each task knows that it has some predecessors and some successors. So as you can see on the screen in this exemplar representation of task networks, task 3 has to be executed after task 1 and task 2, but has to be executed before task 5. And this structure supports the parallel execution of those actions very well. And as it turns out, goal provided to this algorithm also needs to be a task itself. So we can have, for example, task 6, which would be a goal, and it would be decomposed by the algorithm to such a representation. And it's convenient to do this as such. I will be using the task network as a supportive algorithm, or rather supportive plan structure for this algorithm. And yeah, the algorithm itself. So here you have a very high-level overview how the algorithm looks. It has 4 steps: heuristic filtration of agents, plan selection, team selection, and task delegation step. If task delegation step succeeds, then the whole algorithm succeeds. We have a cooperative plan. Everything is going well. The problem is that it's actually quite rare to have the task delegation succeed on the first try. Each of those steps can fail. And when it fails, the previous step is considered back again with some different approaches to try a different approach and see if anything changes. But if the second step, plan selection, fails, that means that there is no available plan to realize to achieve this goal, and that means that the whole algorithm failed, and we know that the goal is unachievable. Let's get a little bit more into details. So, step 1, heuristically filter agents. The plan initiator, the agent that initiates the planning process, can have some preconceptions about which agents are a good fit for this kind of plan that they are trying, for this goal that they are trying to achieve, rather than plan. And the most obvious example is, well, nobody is going to select an incapacitated team member to, try to execute anything, because they're not capable of that. So there is one reason to filter them out of the algorithm. Yeah. Then we select a plan. And what's important, we need to decompose a goal task into some available task networks. And then we simply iterate through the available tasks networks, try to pass the control to the steps farther down the line, and see if they are succeeding. If they are not, if they returned invalid result, we know that the algorithm failed, and we have to do something different because the goal is unachievable. After that, we have a team selection. One very important thing is that the task decomposition can be done by any means. So you can use the proper HTN algorithm, or like what I did here for simplicity's sake, you can use a plan library. So yeah, there is that. Then we select the team. We iterate through every possible subset of potential team members, excluding obviously empty set, because that's not going to help us at all in any possible plan. And we see if we pass this selected plan and this selected team, if the algorithm succeeds. If it does not, we return to the previous step. The important note is that I try to at first gather the set of the highest cardinality, because it's, especially in games, it's a good way to try, cooperate with actual other agents to cooperate, because this is very possible that the plan can be wholly realized by just one agent, but there is no point to, make computations like that if you can just assign everything to an agent. So at first, we try to delegate tasks to as many agents as possible. Yeah, and then we're on to delegate task step, which is probably the most complicated out of all those four. And right now I'm showing you some pseudocode and example of the process, and then a bit further I'm going to show you some code. So at first we reset the agent's internal planning state so that we clear any leftovers from the previous planning processes and so on. Then we gather all tasks from the provided task network that have no unresolved predecessors. And I'm going to call this collection a frontier from now on. The term is borrowed from the exploration problems, and this is basically a simplified exploration problem. We iterate through all the provided team members and all the tasks from the frontier, and we evaluate each possible combination of pairs, task, and agent, and we take into consideration three parameters: agent's opportunity, ability, and willingness. They mean something. I'm going to tell you a little bit more about them in a bit, but for now, just assume that they are simple numbers. After we evaluated all combinations, we select the pair with the best overall evaluation, and we mark the selected task as resolved, and we apply effects of this task to the internal agent state that was assigned to this task. We repeat steps 2 to 5. The important thing is that theoretically, in step 4, we select the best overall evaluation and the best overall pairing, but the best overall pairing can be not good enough. If our best pairing is not good enough, that means that this step fails, because we didn't manage to assign at least one task. Yeah, then we repeat the whole process until there is no task that is unresolved, or if frontier is empty. And then there is a final check. If we manage to delegate tasks in such a way that each task is assigned to an agent, and each agent has at least one task assigned, then the planning process succeeded, the delegation step succeeded. Otherwise, it didn't. And the figure on the right shows you how the frontier is explored. So at the first step, both yellow nodes are on the frontier because they have no unresolved predecessors, and that is because they have no predecessors. Then in step 2, we select one of the nodes, we mark it as resolved. No new node enters the frontier because they still have unresolved predecessors. At step 3, we resolve the other node, 2 new nodes enter frontier, and so on, so on. Yeah, and here is the code. While there isn't a task on the frontier, we try to assign one of the tasks. If commitment is invalid, the step 4 fails. Then there is some, accounting. We add the commitment to the list. We process the effects of the task. We mark the task as assigned, refresh the frontier, and so on. And there is that final check that I told you. If the number of commitments is equal to number of tasks from the task network, and number of allocated agents is equal to the whole team's quantity. Then we have a proper cooperative plan, and we can work with that. So yeah, here is the method try assign task, how the actual task assignment works. Like I said, we iterate through those two collections. We evaluate all possible pairings. We generate for them those task parameters that I told you a little bit before, and we evaluate them in whatever way necessary. This is developer can evaluate those parameters however they wish. We select the best pairing. If the best score is not good enough, beneath some threshold, then you know the pairing is invalid. Otherwise, we get a valid commitment. For the threshold, I usually use any small numbers just above 0. And yeah, task parameters. By now, you're probably wondering what's going on with those parameters. So the ability determines how physically agent is able to actually execute this task. Opportunity determines the environmental conditions that the agent is going to consider during the potential assignment of this task. The higher the opportunity, the more advantageous is the environment. Willingness tells us how eager and willing the agent is to do the task. And here is some simple example. So let's say that we need to press a button. And we have 3 agents. One is very near the button, doesn't need to walk very far, is actually willing, is very happy to do the task, but unfortunately is tied on the floor. The second one is very near the button, is lazy and doesn't want to do the task because he has better things to do right now, and is completely able, stands on his feet, is capable of handling this task. The third one is kind of far. He would need to walk towards the button to achieve, to be able to execute this task properly. It's willing and is able. And the scores are given us in this table. The agents that are standing on their feet have the ability score of 1. The one that is tied on the floor has a 0.1 because technically, when you're tied, it doesn't mean you cannot move. You're just going to make it very slowly towards your goal. You can crawl with your teeth, for example. Agents that are near the button are given the score of 0.9 because they technically still need to move, but you know it's very near. And the agent that is far is actually not that far. It isn't days walk from there. It's just a few meters, so the score is 0.5. And willingness is assigned 1 for the agents that are willing, and the lazy one really doesn't want to do this, so the score is 0.2. And the evaluation, the exemplar evaluation that I'll be using here is simple multiplication of all those numbers. And as you can see, the highest score is given to the third agent, 0.5, and the third agent, if this situation would be included in the planning process, the third agent would be selected to be assigned to this task. So yeah, some problems I encountered along the way. Let me first explain you the situation that I will be working on. So I want the agents from Fugitive 5 to make a coordinated assault on the building. I want them to, each of them, to approach their nearest doors. Then after each of them approaches the door, they need to rotate towards the door to be able to see into the building if this door suddenly opens. Then, when all of them are in position, I want them to enter the building, and then each of them can search the building in search for the player character. So the situation that I want to get looks like on the diagram on the left. We have 3 agents ABC, and we have 3 doors, 1 to 3. And I want agent A to be assigned to door 1, B to 2, and C to 3. Yeah, and that was not working like that, the first iteration. So the delegation algorithm, the thing that I described you in the step 4 of the call algorithm, worked differently within the first iteration when I tried to develop this solution. So the difference is, at first, I tried simply to consider one of the nodes from the frontier, and then I iterated through the team members, I selected the one that was given the best score and assigned it to the task from the frontier. Then I considered the next task from the frontier, and so on until the frontier was empty. The problem is that it was very heavily order dependent. Depending on in which order tasks were put into the task network, the result was different. So for example, in this situation, and this is what actually happened, the door number 1 was considered at first. And as it turns out, the agent A is actually quite far from the door 1. And the one that was the closest to door 1 was agent B. And very obviously, I coded the game as such that you cannot assign one agent to more than one door because that would completely not make sense. So the agent B is then excluded from the set of from agents that can be selected to fulfill the other paths towards the building. Then the next were the door 3. And from agents A and C, C was the closest. And then the only door that were left were door 3, and agents A had to walk around the entire map to, approach the door that were assigned to them. And it wasn't really that good. But the solution was, like you can probably imagine, the thing that I showed you that is actually working. I made it less greedy. I'm evaluating all possible combinations of pairing tasks and agents. And this is how it works like right now. That doesn't differ very much from the previous video, but they will manage to assault the building just by the two of them. So situation is the same. Norman here devises a plan, approaches the door. Oh, sorry. This is the first video. This is the first case where you see the planning algorithm working. So Norman devises the plan. They all approach the doors simultaneously. None of them enters the building. And only all of them are in a proper position. They enter the building and start shooting my player character. Yeah, looks very good with those animations. So yeah, kind of works, but there are still edge cases. So the problem is that, okay, it's less greedy, but it's still greedy. In case of this example, when I simply move the agent A towards the right, near the agent C, the ideal situation would be for them to simply shift left and all of them to take care of the door on their left. Unfortunately, when this algorithm is executed, the best pairing is selected first, so agent B gets assigned to door 2 at first. Then agent C gets assigned to door 3, and then the only option that was left is agent A towards the door 1. The agent A still needs to walk around a bit, but only one agent has subpar assignment. The rest of them looks okay. So it's still a vastly better solution than the one that was before. And you can ask why I don't try to make it as in the ideal situation. And mostly because of combinatorics. The complexity of computations would completely explode. I would need to consider all possible pairings in all different combinations. And it's quite a lot even in that simple plan. So it's not possible. I have an idea how that can be fixed, but it's very experimental and it's going to be said in the chapter for potential improvement. The other major problem was subsets of agents. So yeah, it works fine when I have 3 agents and 3 doors. What is going to happen when I have only 2 agents? Because they are not able to fulfill the plan that I showed you before because they need 3 agents for 3 doors. So obviously, I generate plans for 2 agents. But the problem is there are 3 of them. I can consider door 1 and 2, door 2 and 3, or door 1 and 3. And which one of them should be selected during the plan selection step, which is before I even start to evaluating those task delegations. So that was a bit problematic. And the solution is kind of obvious. I need to evaluate different plans and select the one that gets the best total evaluation. So after calculating the first viable plan that returns a proper cooperative plan, I consider the n next plans, and the n is configurable, whatever you wish. And then I evaluate those plans based on scores of all commitments, based on those task parameters, and I simply select the best one. The problem is that the evaluation wasn't really that obvious because I don't know what the plan includes. I don't have any metadata of the plan. Or I would need to, do a lot of conditional checking for every possibility in the game, which is not appropriate. So the things I tried at first was average. The problem is that average in this case favors shortest plans because we try to assign best possible evaluation. It means that the next assignment that is going to be added to the plan actually worsens the score. Because the lower score, the next score is lower than the one that was there before. So the average results in shortest viable plan. This is not necessarily the best one. Sum is the other way around, simply favors longest plans, which is also not acceptable. Min is kind of weird because I thought, okay, min usually works when you try to evaluate some things. But the problem is that the worst possible assignment from a selected plan is okay, because we try to maximize the worst case scenario. Problem is that we do not consider any of the rest of the tasks. So the worst case scenario is okay, the rest of them are basically random. And it's not looking very pretty, looks very stupid. So the good default that I decided to use is sum of all scores of all commitments divided by maximum number of tasks assigned to a singular agent. It basically works like I was expecting average to work. There is also other possibility, sum of scores divided by the length of critical path from the task network, but this one is simpler to calculate and they are probably going to give similar results. So yeah, plan execution. Same situation, but after my colleague Norman comes up with the plan how to kill my player character, I am going to be first and kill him first. Therefore, only 2 agents are left, and they need to make do with the plan without one of their colleagues. So what happens? For now, they continue with the plan because they didn't get in contact with Norman yet. They don't know that he will not respond, but now they do. When one of them finished one task, Sebastian was selected as new plan initiator, calculated a new plan, and they assaulted the building without Norman. So that situation works. And yes, that were the 2 biggest hurdles that I encountered during the development of the solution. I'll show you a bit of architecture. I was too lazy to make UML diagrams, so you're going to see some code and some method signatures. There is one interface, plan provider. Singular responsibility of this interface is to decompose the provided goal task into available task networks. Then we have the task network, obviously, which consists of list of tasks and their pairings, their orderings, which are pairs of predecessor and successor. And I plan to also include the possibility to merge the task networks to make it possible for the algorithm to work hierarchically, but yeah, in a bit. There is a task, and as you can see, the task has a name, is assigned to a plan, is able to calculate the task parameters, the ability, opportunity, and willingness, has to be able to calculate the status as known by the particular agent, because the agents do not have to have a perfect information. They can have some pre-assumptions, they can be stupid, or they can lie. So there are a few possibilities to calculate those. Process task and task assigned are very similar, but the process task is called when the agent tries to execute the task after the planning concludes, while the task assigned, which is, it turns out, not a very good name for that method, but well, I have to live with that for now, is responsible for applying the change, the effects of the task to the agent's planning state, which will be used during the planning algorithm. And then we need to determine whether the goal even makes sense. If this task is treated as a goal, we need to know whether there is even a point to realize it. For example, if this building would be burning, there is no reason to try to assault it because, well, the player character probably is going to be disposed anyway. Cooperative plan, the structure that defines the successful plan. It has a goal, it has a task network which will be used to achieve this goal. It has an initiator, an agent that initiated the planning process. There are team members which are assigned to the commitments, and the important thing is that initiator does not need to be included in the team members. They can also delegate to other people only. And then there are commitments which are pairings of tasks and agents. And commitment also knows which supervisor supervises the execution of this commitment. There is a status of the commitment and task parameters for the sake if we ever need to reevaluate the commitment or the whole plan. There is a cooperating agent, and it is an entity that is responsible for execution of the plan, of the cooperative plan. Not necessarily formulating the plan. The plan formulation is the responsibility of the supervisor, which is connected to the cooperating agent, as you can see. And there are some callbacks because agent can try to contact the supervisor to let them know, okay, I'm done with this task, and they get no response. If they get no response, they need to select new initiator, and I've exposed some events for the developer to be able to react to it. So yeah, there is events, connected supervisor, list of plans that are executed by this cooperating agent. There is a world context which gives, environmental context for the planning process. And the entity has to be able to determine the plan status given its environment and its knowledge. The agent has to be able to report the tasks, the selected tasks to the supervisor. Task needs to be evaluated by the agent given the parameters, the task, and the plan which this task is going to be a part of. Reset agent states is responsible for resetting the planning state. Update assignee task status updates commitment statuses, and there is a method for selecting initiator when contacting the supervisor phase. And then there is the last class, cooperation supervisor, which is responsible for whole planning process, apart from what you can see here. There are a lot of callbacks because, like you noticed, the planning can go either way. It can succeed, it can be abandoned, agent might not be responsive, planning fails, so the developer needs to react to all those situations. There is a plan provider, which is responsible, like I said, for decomposing the goal task. A number of plans which will be considered after the first viable one. Planning queue, list of supervised plans, then methods for queuing the goals to the planning queue, processing the planning queue, updating statuses of the supervised commitments. Preprocessing team members is responsible for the first step of the algorithm, heuristic filtration. We have to be able to obtain the whole plan score for the sake of the evaluation with those subset combinations, like in the previous problem. And it both needs to be able to broadcast the updates to other team members when it receives some report, and formulate the plan, which is basically the core of the whole presentation and the solution. So yeah, interaction with game AI. Because like I said, this is not a solution that is supposed to be used instead of the game AI. This is a module that can enhance the game AI, but will not work by itself. You make it work by itself, but it's probably more work than it's necessary to make the game enjoyable. So I decided to use some higher level AI, which switches those AIs, the normal one and the cooperative one, back and forth, depending on number of factors. So I know that we have to switch to normal game AI from the cooperation whenever there is no available plan, because obviously there is no point, when each plan is completely done, and there is probably some custom conditions that the developer wishes to implement for the AI to be more reactive, not just blindly follow the plans when something unexpected happens in their environment. I have few videos from Fugitive 5 that will walk you through those situations. So yeah, still the same situation. Norman comes up with a plan how to assault the building, approaches the door, and gets killed. They continue with the plan. They try to contact Norman. Norman is dead, therefore Sebastian is the new initiator, and will try to devise a new plan, but Ezekiel is also killed. So there is planning process failed, and there is no available plan. Therefore, Sebastian went back to his normal AI and is doing patrol routes right now. In a proper situation in game, you would probably prefer to react in some way. For example, investigate why one of the team members isn't reacting to you. But you know, this is a simple test case. There is no other agents that could help with the whole situation. So Norman decides to run with his life. Sebastian, sorry. Yeah. Then there is a situation when plan gets done. In this one, I enter the building. Norman notices me, but then I exit unnoticed through the other door. And they still assume that I'm in this building because they have no information suggesting otherwise. Norman comes up with a plan, and they try to execute it. And they search the building because they do not see immediately my player character. And as you can see right about now, the titles for the task names disappeared. It means that they are back to their normal AI, and they are trying to investigate to find my player character. And yeah, they're back to their normal AI after a while. If they won't find me, if they don't find me, they will go back to their patrol routes. And the third case, custom conditions. So I wanted enemies to react to sight of my characters. I don't want them to simply ignore my character walking right through them and continue towards the door, because that would be nonsensical. So whenever one of the agents sees one of my characters, they stop responding to the initiators and other team members, and they just decide to pursue my character and try to make him dead. And they tried to communicate right now. Ezekiel is not responding. The planning process is beginning anew. And as you can see, Ezekiel is doing his stuff, and Norman and Sebastian are continuing with the plan. The important thing is that if the player character is noticed inside the building, the plan is not abandoned completely, like in case of noticing someone outside the building. It is suspended. That means that when I disappear from their line of sight, they are going to continue their plan. If I would be designing the proper game situations, I would probably tackle it a bit differently, but I wanted to show that the plan can be suspended. Okay. Potential improvements. Because the algorithm works, but I would like it to do some more things. Like, for example, I would like it to support different topologies. Because for now, as some of you may have noticed, technically, it would be possible to have many different supervisors for the same plan, but untested for now. And I would like them to be able to plan hierarchically. That means that one of the agents decomposes a task, delegates those tasks to other team members, and those other team members decides, I know the other decomposition. This task can also be simplified, and they decompose their task, and then delegate those to their subordinates, and the star gets more complicated. Or even it should be possible to have simply multiple agents supervising other colleagues. Like, for example, you have some captain who says, okay, so you're going to do this and you're going to supervise them because I don't want to do this. So there is that. I would like the algorithm to be able to better handle unresponsiveness, because right now, if, as in this picture, two agents are in the position and they are ready to assault the building, and the third one shows no signs to even trying, the algorithm should allow the agents to say, okay, so this guy is obviously not going to help. Let's try to make do without him. You can do this by some custom logic in your game, but I would like it to be handled a little bit more by the algorithm itself, because that's probably possible. And there are some other minor stuff. For now, I have no task constraints, and I do constraints by proper scoring of the tasks, of those task parameters. But it would be much easier if I could say, okay, so task A should be done by the same agent that is assigned to task B. Like, for example, with the approaching the door rotation towards those doors. Simulated task delegation is the idea that is supposed to potentially handle the situation, the edge case that I was showing before. I want to try just to do some bunch of random assignments, tasks to agents, gather lots of statistical data, and it's like the best evaluation from those, and see how this compares to the current solution. Technically possible one, agents with no supervisor that can be a part of the plan but cannot plan by themselves, which is probably a situation that would be encountered very often in games. And then I would like to see what happens when multiple entities try to execute multiple plans in parallel. But that remains to be seen in near future. So that's more or less everything I wanted to show you. Here is some bibliography if you're interested in the subject. There is a book, Teamwork in Multi-Agent Systems, A Formal Approach. This is the book on which I based this approach. The whole algorithm, very similar algorithm because I modified this slightly, is described in this book in, very formal approach. This is a very mathematical book. And then there is a YouTube playlist which is uploaded by University of Edinburgh, and it is a very good AI planning course. So if you're interested in the GOP or HTNs, it's a good way to know those algorithms. Some obligatory slide that I had to put here. And thank you very much for listening to my talk. If you want to contact me, here is my email and my Discord handle. And if you have any questions, feel free.
How do you handle memory and communication? Like, obviously, in the case of your game, communication is simplified because, as I understood it, agents communicate over the radio, so they don't need to see each other to pass the info around. But like, how much do they remember, and how much of it is used during the planning process?
Okay, so honestly, in this case, not a lot, because it didn't need a lot of memory. They just need to know which of the other team members are alive and if they still consider the player character to be inside the building. But there is a thing that I showed you here. The cooperative agent has a templated member called world context. And this is basically everything that this agent knows about its environment. And it also can contain the agent's memory, the agent perception, or the agent's delusions, even if you want to model that. So everything that you need agents to remember, you can put simply in there. And it can be anything that you want because it's a templated member.
All right. And when, for example, an agent sees the player, this is stored, and for how long it is stored, and do you store actually like multiple instances of these events, like seeing the player?
Okay, so in this case, when the player character disappears, I store that this character is considered a disappeared one, and I queue one of the supervisors a goal to search for this player. So if the planning process either fails or succeeds, the data about the agent is erased because we know that he isn't there, or at least we think that he isn't there because the agents, can be mistaken about that. The player character could be still hiding in the building, but hidden. And then if this agent becomes otherwise cited, then also this data is erased from their knowledge because they know where the agent is, so that there is no point to go to their previous position.
So you only store the current knowledge, like global knowledge about whether the player is seen or not?
It's not a global knowledge. It's a local knowledge per agent.
Ah, okay.
Each agent has its own perception memory and his own preconceptions about his environment.
Okay, thank you.
Yep, no problem.
Yeah, so I have a question about whether this system could basically support a plan within a plan. So if we consider one of the tasks to be basically come up with yet another plan.
Yeah, that's exactly what I said that I will be working on next with those different topologies, because that's exactly what I'm aiming for. Because the goal is given as a task, therefore it is decomposed as list of tasks, and there is nothing preventing you to decompose those tasks further. But I haven't tested it yet, and I would need to handle recursivity of it itself. It's probably not very hard, but I prefer it for now to polish what I have than do very broad strokes.
Okay.
Do you think it makes sense to take players' actions into consideration while planning, or it will just overcomplicate everything?
In this game, it would probably overcomplicate things because, well, like I said, the game is not very good and not that complicated. But I can imagine situations where you should take player actions into consideration. So, for example, if you have some very complicated real-time strategy, and there is a fog of war, and you know that they moved their unit somewhere there, and they, for example, you notice that they have the possibility to gain such resources, and those resources can be used to build a particular type of building right there, then it is very possible to take this into consideration and, for example, give this planning algorithm a goal for scouting that location, or even preemptively trying to assume that this building is there and try to destroy it with proper units.
Another question, because in your example, it was desired to continue plan even if player left the room, right?
Yeah.
But I'm wondering if you have cases where you actually want to make it invalid, and do you reevaluate plans more often, and how do you decide that, okay, this plan is more important? Is it some threshold or something?
So you can base it on the plan evaluations. You have all available data to evaluate those plans again, and you can prioritize the plan based on the evaluations. You can have some metadata assigned to the goals. So you also can, as a developer, decide that, okay, this goal is much more important than that one, and therefore you should put more focus there. Sorry, I forgot the second part of the question. Could you repeat?
I don't think there was a second part.
Okay, so I probably wanted to add something, but short-term memory is is a thing. Yeah.
Thank you for the amazing talk. Very interesting. I was hoping to ask you about how you tested this system.
With this game, can you be more
When you
precise?
were developing the logic for this, did you like go by unit test and test it in isolation, or did you have some sort of a headless solution where the system played through different scenarios and then you maybe read logs?
Okay, so this situation was very manual, specificity of this game, and I didn't really want to bother with the a better solution. But I also have a separate repository with only this algorithm without the game, and I also have a lots of unit tests with some simpler test cases. But I also wanted to test it on real organism, a game, because it's much harder to model time constraints in unit tests. So yeah, I have both manual and automatic tests. Okay, so that's probably all of the questions. Thank you very much for listening. And yeah, if you want to get in contact,